Okay, in today's lecture, the most important thing about today's lecture is the conversion or transformation between coordinate systems, and it can be divided into two jobs. One is the conversion of a point in the space between coordinate system. The other is the conversion of a vector in the between coordinate systems. So the first one is relatively straightforward, and I believe that you have done that before. The new thing is the conversion of vectors representation among different coordinate systems. So in this slide, we have equation 1.46a and 1.46b. What is the usage of the two equations, the two sets of equations? The first set is actually the conversion equations for points on the cylindrical coordinate to Cartesian coordinate. And I believe that in your prior studies, you must have, or you must already know how to convert coordinates from polar coordinate systems to Cartesian coordinate system and vice versa. Say you have a point in the polar coordinate systems as r equals to 2 and phi equals to 30 degrees. So what is the representation of this point in the Cartesian coordinate system? That will be r times cosine phi and r times sine phi. And because cosine of 30 degrees is what? Square root of 3 over 2. And sine of 30 degrees is 1/2. So you have square root of 3 and 1 in rectangular coordinate systems. Where so they are both refers to the same point. However, one is expressed in the cylindrical coordinate system and the other is in the Cartesian coordinate system. All right. So equation 1.46a is essentially what we have done for the conversion from polar coordinate system to rectangular coordinate system. Of course, you can convert the representation of point in Cartesian coordinate system back to the polar coordinate system. So what would that be? To do the inverse conversion, the r equals to the square root of x-axis and y-axis, and the parameter phi is what? Is the arctangent of y over x, right? And now that the order matters, this order matters. And for the conversion between cylindrical coordinate system and Cartesian coordinate system, the cylindrical to Cartesian one is 1.46a. How about the inverted one, that is 1.46 A, and well, it's essentially the same as I wrote on the blackboard. So let's move on to the other set, is the conversion between spherical coordinate and Cartesian coordinate. So it's a little bit complicated, but it's essentially follow the same order, same fashion. So X will be the cosine phi times the projection of the vector connecting from the origin to the observation point, and find its projection on the xy plane, so that will become r sine theta. So using the projection r sine theta and taking the cosine of 5 of this will yard the x coordinate, and the y coordinate will be r times sine theta times psi phi, and the projection on the z-axis will be r times cosine theta. So you need to look at this figure very carefully to see all the relationship between vectors projection on specific planes. So here, another thing that I will notify you is, you see in 1.46a, the r has a subscript of c, which refer it as the radius on the cylindrical coordinate system. And for the radius r in the spherical coordinate system, it comes with the subscript s. So it specifies the difference between cylindrical coordinate and spherical coordinate. And for the conversion from Cartesian to spherical coordinate system, the 1.747b give you the 3 essential formulas. So you have Rs equals to the square root of the square sum of x, y, and z, and theta is arctangent of this over z. So what is this? This is the projection of the point of O, is the projection of the vector from the origin to observation point on the xy plane. Okay? So the projection divided by z and taking the arctangent of it shall give you the theta angle in this position. And the cosine of it will give you the cosine of this, I'm sorry. The arctangent of y over x will give you the phi angle in the spherical coordinate system. Okay? And the final thing that I have already notified you is you need to think about this. Okay? So what is the answer of the first one? Well, in the denominator is y-axis, and in denominator is the x-axis. So this is actually what? What is the answer of this? Minus 45 degree. Okay? Minus 45 degree. And how about this one? It's 135 degree, right? So this is the position of the first point, and this is the position of second point. The y over axis value are both minus 1. However, if you follow the rule of arctangent, this shall give you minus 45 degree, and this shall be 135 degree. Okay? So there are a slight difference. And And the difference matters when you're using the calculator. Okay, be sure that you know the difference. Okay, when you calculate the do the conversion using calculator. 所以要学会在计算机的时候能够正确的分出这两个 case 哦。Alright, so the conversion of points among coordinate system is relatively straightforward. The more interesting part is the conversion of vectors among coordinate systems. So here are some basic about what we are going to do for the conversion of vectors among coordinate systems. So equation 1.48 ABC are 9 equations. That is the scalar product of reference direction in both cylindrical and Cartesian coordinate systems. So you have AR dot AX, AR dot AY, and AR dot AZ. What are the implications of this result? This result tells you that AR and AX are somewhat related, or they are coupled. No, they are somewhat related. So the scalar product will produce a value that is the cosine value of the angle between R and X, between AR and AX. And the angle between AR and AY, the sine of the angle will produce the projection of AR on AY. So you can understand it as cosine phi will be the projection of AR on AX, or sine phi is the projection of AR on AY, or vice versa. Say sine phi is the projection of AY on AR. Both of the two statements make sense. So how about this result? AR dot AZ always equals to 0, which means the two reference directions are not coupled. They are always orthogonal, always perpendicular. So they will be 0 at all times. Okay? So these 9 equations kind of give you some indication about the geometry between the two sets of reference directions. So now that the footnote over there kind of summarize what I'm going to say in this slide. And you can do the same thing for the reference direction in spherical coordinate and Cartesian coordinate. So as you can see, the only thing that comes with 0 is A phi dot AZ, which means they are always perpendicular to each other. For other reference directions, there are some coupling can be found in terms of theta angle and phi angle. All right? You don't have to memorize this matrix. Okay? You don't need to memorize this matrix. But you will definitely see the application of these equations in your first midterm. But I will provide you with these equations. You really need to know how to use them, and you better practice how to use them when doing your homework. Okay? All right. Okay, so the second thing that I need to remind you is to memorize the definition of reference direction, in particular for reference direction in cylindrical and spherical coordinates. Okay, so what is the definition of reference direction? It's always pointing toward the direction with larger value. So AR direction is always pointing away from the origin or away from the z-axis in the cylindrical coordinate. Okay, so well, that one is easier. So for point P, it's AR direction. Positive AR direction is in this way. And the next thing is, what is the A theta direction? So you need to record that theta equals 0 is in which direction? It's in the positive z direction. And the theta number becomes larger and larger as it moves away from the z direction toward the minus z direction. So for point P, theta value will become greater when it goes downward, goes this way, and becomes smaller values this way. So the positive A theta direction should be as marked on this figure. Now it should be pointing to the bottom right direction on the slide. Okay? Now be sure to understand the definition of A theta direction. How about Phi direction in this plot? So Phi, where is the phi equals to 0 direction? Phi equals to 0 at the positive x-axis. So on this line, phi equals to 0. On the positive y direction, phi equals to 90. So for point P, the A phi direction is actually pointing this way, to pointing to a larger phi value. Okay? So be sure to why I stress the importance of this definition. Because in this matrix, you have some minus sign, some positive sign. The positive sign and minus sign actually comes from the definition of these directions. So when they are aligned largely toward the same direction, they end up with a positive value. But if one of the vector is kind of pointing toward the back of the other vector, it ends up with a negative sign. Okay? All right, so here are 4 metrics that I will provide you during the midterm test. There are 2 sets. The 2 ones on the left are conversion between spherical and Cartesian coordinate system. The 2 matrices on the right are conversions of vectors between cylindrical and Cartesian coordinate system. So as you can see, the order of fx, fy, fz, and fr, f theta, f phi are swapped in the 2 set of matrix representation. And the matrix, what are the difference of the 2 matrices? They are quite similar, but they are not the same. They are in what kind of relationship? They are the transpose of the other. Transpose, which means you invert the order in terms of the with respect to the diagonal with the downward direction. Okay. So the same rules apply to the conversion of matrix between Cartesial and cylindrical coordinate system. So in the two equations to the right, you can see the transpose more clearly. So these are the four matrix equations I shall provide you during the midterm test. But let's using the example on the textbook to show you how to do the vector conversions between coordinate system. So example 1.5 wants you to perform conversion of a vector in which coordinate system? In the Cartesian coordinate system, which is 3ax plus 4ay plus 5az. Now that this description only specifies the direction of the vectors, these vectors can be placed anywhere in the space. However, the problem also states the position of this vector is placed at 3, 4, 5. And this description is critical because the conversion may be different or shall be different if the vector is placed in different position in the space. So the position 3, 4, 5 is important. So both the position and the vector descriptions are critical toward the solution, toward the result of vector conversion. So first, let's follow the description on the textbook about how to perform this conversion. So the first thing is convert the point, convert the position from Cartesian coordinate to spherical coordinate. So the position is 3, 4, 5, and you can easily using what? Using equation 1.47b to find out r equals to 5 times square root of 2, theta equals to 45 degrees, which is 1/8 of pi, pi over a, 8分之 pi 了，45 度. And phi is what? Phi is the arctangent of 4 over 3, so that shall be 53 degrees. Okay, so using these equations, you can find out the conversion of point easily, relatively easily. The second thing is apply the conversion matrix to find out the result, the conversion of the vector. Now that the matrix used in the conversion matrix used in the textbook is different from what I have for you in the midterm. Okay, and I will show you both approach. You can decide which one makes you easier to understand. Of course, you can choose any one of the two to do the problem in the homeworks and the test. Because the two methods are, well, they are both correct. It's only different depending on how you understand the problem or how you interpret the muscle. 看你怎么样解读那个方法了所以其实课本上讲的方法跟我喜欢的方法其实刚好相反但我 你用的对的话，结果都是对的嘛，哈。但你自己可以决定一下哪个方法你觉得比较合理啦，哈，比较容易懂，哈，容易懂得了，那当然是最重要的啦，哈，可以把问题解决。All right. So you still use the matrix that we have seen in previous slides. That is, AX, AY, and AZ can be found by AR, A theta, A phi times the conversion matrix shown here. The conversion matrix is made up with the scalar product between AXYZ and AR theta phi, like this. So what is the implication of this result? So the first thing, because in the previous slide we find out R equals to phi times square root of 2 theta. Well, this one is important. Theta is 45 degrees, phi is 53 degrees. So the sine theta values, cosine theta value, cosine phi value, sine phi value can be found using 45 degree, theta equals to 45 degree, and phi equals to 53 degree. So the first term will be 0.6 times square root of 2 over 2. So here, 0.3 times square root of 2 is actually the sine theta, which is 1 over square of 2 times cosine phi. Phi equals to 53 degrees, so it's 0.6. So this is the product of 1 over square root of 2 times 0.6. Okay? And the second term over here is cosine 45 degree times cosine 53 degree. That will be 0.6 times 1 over square root of 2. So you end up with 0.3 times square root of 2 as well. And the third term is minus sine of 53 degree. So that's minus 0.8. Okay? And using these values and times AR, A theta, A phi. So what is the implication of this part? Because for matrix operation, you know that this means AX equals to 0.3 times square root of 2 times AR plus 0.3 times square root of 2 times A theta minus 0.8 times A phi. Like these things in the parentheses. So what is the implication? What is the meaning of this equation? The meaning of this equation, interpreted from my own perspective, is one portion of AX can be found or can be synthesized by 0.3 times square root of 2 portion of AR times this value of A theta and this value of A phi. So this equation provides you a conversion between or a synthesis method. 什么是 synthesize 或 synthesis？ 合成嘛，组合的嘛，所以意思是什么？意思就是说，一份的 AX 可以由 0.6 根号2份的 AR 跟0.3了，0.3根号2份的 AR， 0.3根号2份的 A theta， 还有负的 0.8 份的 A phi 组合而成。那在这一个题目里头，你总共需要几份的 AX？ 你需要3份啊。那第二句话告诉你说，一份的 AY 是由 0.4 根号2份的 AR、 0.4 根号2份的 A theta、 0.6 份的 A phi 组合而成。这里需要几份？4份，所以前面乘个4。那第三个式子呢？一份的 AZ 是由 0.5 根号2份的 AR 减去 0.5 根号2份的 A theta。 组合而成，而这里需要5份啊。所以那因为 AS、AY、AZ 都是由 AR、西塔、A5 组合而成的，所以你可以把它们后面这9项啊，事实上是8项了，把它重新组合一下。那重新组合的结果，你发现什么事 ？A 西塔跟 A5 被抵消掉了。好，这题目的答案看起来很整洁啦，但是我不是很喜欢哈，原因是它挑了一个345的向量摆在345这个位置，它让结果变得很简洁，但实际上问题是有一点复杂了哈。所以我等一下会把题目稍微再改一下哈，稍微再改一下，让你看一下，看出一些不同的效果哈。少了 A 西塔没有？对啊，它所以这边没有 A 西塔，没有 A5 是刚刚好的状况了哈。正常来讲，其实应该要有。好。Alright, so that's one way to interpret this method, this approach. So let's look at the result. So for 3ax plus 4ay plus 5az, when this vector is positioned on 3, 4, 5 direction, the vector direction happens to be align align 是什么意思 ？align 是平行了哈，刚好贴合哈。align with the direction from the origin to the observation point. So as you can see, the red arrowhead and the black arrowhead are in parallel. So as a result, the vector converted result is relatively simple. It's just 5 portion of AR. So it's a beautiful answer, but I'm not fond of this answer because it's kind of simplify the process, simplify the result. So as a contrast, so let's modify this problem a little bit. Say we have the same vector, 3ax plus 4a4i plus 5az. However, this time the vector is placed at a position of 4, 3, 5, a somewhat different position. So what is the first step? As my remarks put on this slide is find out the converted position, find out the description of the position in the desired coordinate system. All right, that is, you convert 4, 3, 5 to spherical coordinates to what? In cylindrical. I'm sorry. So I twisted the problem a little bit more. Okay, so this is a conversion between cylindrical coordinate system and the Cartesian coordinate system. All right, so 4, 3, 5 after the conversion is 5 as r, 37 degree as what? As 5 coordinate. And the z coordinate remains the same, that is 5, using this relationship. The second step is find out the transformation matrix. This time I use my own approach, that is the format one. I choose one of the 4 matrices I wrote in the previous slide. So after substituting the 5 value to find out cosine phi, sine phi, minus sine phi, and cosine phi, you have this matrix. All right? Well, you need to check out my slides when you review your slides at home. Okay, be sure to check the values. So that will be 0.8, 0.60 minus 0.6, 0.80001. And now that in this matrix I have fx, fy, fz on the right hand side and fr, f theta, f phi. So I use the transform matrix T times fx, fy, fz, that is 3, 4, 5 in the right column. And it shall give you the converted vectors in the left hand. That will be 4.8, 1.4, and 5. Note that when it comes to conversion in Cartesian and spherical or cylindrical coordinate system, it actually makes more sense to use pi instead of degree. Well, you can say that about 400 or 500 years ago, actually the French are more advanced in terms of mathematics with respect to the English. Okay? So, however, we are more accustomed to degree, but actually it makes more sense and it becomes more straightforward in terms of mathematic operation. When it comes to angles, you should use radian instead of degree. Okay, so the value 1.4 in the middle of the vector is actually refers to the radian. It's not a distance. It's a radian. It's a radian value. All right, which is about 80 degree. Okay, about 80.2 degree. Okay. So what is the interpretation of this equation, of this approach? It can be understood as how much AR, A phi, and AZ can be synthesized using 3 portions of AX, and the 4 portions of AY, and the 5 portions of AZ. So this equation can be understood like with this remark, which is a little bit different from the method described in the textbook. Okay, I prefer to adjust the procedure a little bit, so it makes me easier to comprehend, easier to understand the significance of this operation. But it depends on you to choose an approach, to choose a method that you feel more convenient with. Okay? 所以两个方法你都看一看吧，看你觉得哪一种解释你比较能够接受，比较，其实两个方法都对了，OK? Alright, so we can move on to our next topic. So in section 1.4, we will introduce or try to differentiate the difference between scalar field and vector field. As I already mentioned in the first lecture, that in the electromagnetics we are dealing with scalars and vectors. But more importantly, we are dealing with fields. 场嘛，讲中文讲场哈。The fields are descriptions about a physical parameters. So for electromagnetics, the most fundamental physical parameters are electrical field and magnetic fields. So they are real physical phenomenon that we can observe from the nature. And however, in the development of many science topics, and as well as in the development of electromagnetics, we adopt some descriptions or some definitions that are they somewhat like they resemble some physical parameters. They look like physical parameters, but they are not actual physical ones. For example, voltage is not real. Do you believe that? When you study the electric circuits 4 or 5 years ago in your high school, of course you learn a voltage. But do you know that electrical voltage is an imaginary physical parameter? It's not a real one. 电压不是真的哦，电压不是真的。电压其实是电场乘上距离，有听过这种讲法吗？对不对？电场是真的，距离也是真的，电场乘上距离就变成电压，而电压其实它不是真的。当然了，你说那所有的仪器量起来，电表什么量起来不都给你电压吗？对啊，但它其实是电场乘上距离的结果了。所以电压这个东西the so-called electrical voltage is the actual name for electrical voltage can be electrical potential. 电位有没有听过 electrical potential? Or more specifically, in the study of electromagnetics, we can refer voltage as scalar electrical potential. 电存量位能scalar electrical potential. So because you have the name the electrical scalar potential, so you actually have an electrical vector potential. You have a magnetic vector potential. You have magnetic scalar potential. So you actually have at least four potential in the electromagnetics. And potential refers to that this is actually not a real physical quantity. It's an imaginary one that makes our life easier because it's easier to handle the operation using potentials. But we will come to that later on. All right, so let's go back to these slides. We have fields. So they are physical phenomena. They are physical phenomena. And we are more interested about those physical quantities, physical parameters. We are more interested about their variation. If they are consistent or if they are homogeneous, 什么是 homogeneous? 一致的嘛If they are homogeneous in their space distribution or if they are homogeneous in terms of time variation, then the things becomes less interesting. So in the study of electromagnetics, we are more interested about the time domain variation and spatial domain variation for physical quantities. Okay, so in general, when we comes up with description about physical quantity in the space, we usually write up the description or simplified description of those physical quantities using functions. Say we are interested about electrical field, and we write this description as E, the electrical field, is a function of x, y, and z. What does that mean? It means that the electrical field variation in the space can be different according to the variation in position. The electrical field can be different. And sometimes the electrical field also change as the time varies. So it can also be a function of time. So we say we have 3 dimensions in space and 1 variable in time. So in general, the fields that we are interested is a function of 4 dimensions, but actually it's 3 plus 1, because time and space are not coupled. In general, or in principle. So what are the special cases for time and space are coupled? Well, of course, we have this kind of examples, this kind of instance. For one instance is the Big Bang, okay, at the start of the universe. But I bet that you don't have to worry about that in the rest of your life, okay? And, well, if you live long enough, which is, well, of course, you may have extended lifespans in the future, in the near future. So, if some days we invent spacecraft that approach the close to the speed of light, then you may have some you may have some interaction between space. Well, if you go into a black hole, you may need to think of your physical relationship, because in the black hole, the space and time may be coupled somewhat.